Okay, good morning. Bob Lammon from Phoenix Proto. We're located in Southwest Michigan. And I'm here today to talk to you about aluminum tooling, try to convince you that aluminum tooling is a good alternative to steel. We do have some pretty big players in aluminum. What I want to talk about as far as the characteristics, and that is we have Alcoa here, we have copper brass, we have Clinton aluminum. So if you want to know more about the characteristics of aluminum that I can't answer, we have some pretty big players here that can answer those. I've invited them because I want them to see a lot of the things that we're doing and experiencing in aluminum. Personally, I have over 35 years of aluminum tooling as well as hard steel tooling, so I have some good direct comparisons between both of them. We want to uncover some major misconceptions. We want to review why plastic flows better in aluminum than steel in a lot of cases. We want to cover some of the facts and the myths about aluminum, and we're going to look at some parts and case studies. I've got down there perception. The reason I have that on there is you know, aluminum tooling over the years has really taken a pretty bad rap. It has a reputation for being too soft. Parts that are going to flash, a tool that's not going to wear. You can't run glass-filled materials. You can't do undercuts, and those are all incorrect. The bottom line is that no matter what material you use for the mold, you have some practical keys that are very important. You need a very good solid part design. You have to have the proper mold material picked out based on what resin you're going to use, how many parts you're going to run, and what the part geometry is. And I'm talking specifically about aluminum. And we use a lot of different grades of aluminum. We want to make sure when you're looking at this, utilize an experienced aluminum production mold supplier. Or if you are your own plastic company, work with that mold company that has a lot of aluminum experience. Processors need to be open-minded. You need to make sure that your mold maintenance just fits your good pattern, good industry practices. And make sure, worst case, make sure you utilize a good welder that's using the same rod of material that you're using. So you want a good laser welder. We're going to look at 6 impact areas that will provide us the necessary needs to look at, you know, why is it that we want to use aluminum? What's the main reason for this? What's the big storm about aluminum tooling? And most generally, and these are my experiences, and we do have experiences from other people. We do have a lot of case studies, and we also have studies from other people like major OEMs, your IBMs, your Hondas, your GEs. They have done tons of case studies and years of case studies on aluminum. Most generally, and these are my experiences in a lot of the studies, you achieve a higher, more consistent part quality. Most generally, lower cost for tooling because it's faster. Lower component piece price because of thermal conductivity, which we'll touch on. Part design validation, which you can do just as well in aluminum as you can in steel. In most cases, better in aluminum. Faster to market, additional capacity for motors because you're running a faster cycle. Presentation highlights that you'll see today is downstairs, by the way, we have some molds, some cavity inserts, and we have parts besides those molds. We have a variation of the type of tools that we have down there. We build a lot of tools out of mud units. We build a lot of independent tools. We have some variety down there. So you'll see that, and you'll see the part with the tool. We run strictly prototypes for a few hundred pieces, and then we also run aluminum production tools that may run hundreds of thousands of parts or even beyond 1 million. We're going to look at rapid tooling for prototype samples, like I mentioned, hard to fill resins when you're glass filled, cavities for thin wall sections, your bridge aluminum tooling I mentioned, cavities for high gloss, chrome plated parts, molds with slides, and hot drops. I'm just covering what I see from my customers, and when we talk to people that don't know a lot about aluminum and want to know more, these are some of the most common questions. Can you run any type of resin in aluminum? What we've seen is we're not running steel-filled materials, but we are running glass-filled. So we run up to 40% glass-filled materials in aluminum. But we run all your unfilled nylons, your ABSs and polypro, your High Temp, Temp, and Vectra, which we run. And there's a myth about that. You can't run high temp material or bring your tool above 200 degrees of aluminum. Yes, you can. We run a lot of TPEs, PVCs, santoprines. We have a little clip here that I'm going to show you, and PSG put this on. They specialize in thermal imaging. And we have two tools. We have aluminum tools and a P20 tool. You'll see an A half and a B half for each. They're set on the bench. Over 30 minutes it's taken to get up to 140 degrees using the same thermolator. And after they reach that 140 degrees, they drop down. It takes about 30 minutes to drop down to, I believe it's 70 degrees. So what you're going to see is you're going to see this one and this one right here. These are aluminum, and this is steel. A half, B half. And watch, this is abbreviated. It takes 30 minutes to bring it up to temperature, up to the 140 degrees. Aluminum came out faster, 5 times faster than in P20. And when it cools down that much faster than in P20. So that's one benefit right there, is that does show you the thermal conductivity between aluminum and steel. I do want to touch on glass-filled resins because some of the presentation will cover this. And we do have an aluminum production tool downstairs that's run over 150,000 shots. It's a 2-cavity, 300,000. To date, we're going to run 500,000. You do have options when you're running aluminum and running glass. And that is you can case harden it. You can insert in steel, which we've done. I'm going to show a little bit of a clip here of a rifle that just happens to be gun of the year. We produce 20 to 30 different components for Ruger. In this particular example, I want to show you there's 8 different components that go to this gun. And all the resins are glass-filled materials. And they estimate the volumes to be around 50,000. For 5 years, we run over 100,000 to date. Mechanical slides, hard-coated, so this is a production tool for them. This is a Mag 3, 5, and 10 millimeter. These parts right here that go to the rifle. And then the dust cover and the mag plate. And the follower and retainer. And then there's a trigger guard. And we'll go right into the clip to show you some of the components. And by the way, this clip, apologize, there is some volume to it. We're unable to see it, but in a way I didn't want to really bore you with a lot of the things. But it does talk about the advantage of this rifle for these guys is it's lightweight. And it's lightweight because a good portion of it is plastic. The handle's plastic. At the back end for the pad up against the arm, that is actually a TPE material, which we provide also. Because we're not able to hear some of it, we can go ahead on that later and push ahead on that. Some of the other areas I want to show you about some critical areas, glass-filled materials. There's a 15 to 20 thousandths wall thickness area here, glass-filled materials that we run. We ran over 10,000 parts in aluminum. It was not hard-coated. We run some 2 and 3 shots. The first shot's is a PC, clear PC. The white is the ABS indicator, and then the third shot is a soft PVC. And to date, those parts we ran about 120,000 total. Those are actually single cavity tools. This is an all-temp material. What we do is we use heater cartridges to bring it up to temp. We do not use oil. Second question, can you achieve good surface finish in aluminum? Are you able to achieve a good grain or texture much like you can in steel? And are they consistent? What we've seen is that we can achieve a Class A surface. We can achieve a great grain, and it's not going to wash out. You have options. You can also hard coat it. As far as the surface hardness, the reason why we like to use that, if we bring it up to a Class A, they use that for the final, what looks like a chrome plating. We use what's called NIBOR. And we use a company out of Chicago called Bales that specializes in this, and this helps it bring it up to a Class A surface. And we'll show you. We actually do have some examples downstairs, You're actually able to see a Class A surface in aluminum, and actually the tool that's running in the press today has a Class A surface. This part is a DVD button, and it was chrome plated. So this was run out of, these buttons right here were run out of a ABS, gray ABS plated rolled material. And then it was chrome plated, Class A surface. This just happens to be a lens that if nobody is, if some people are not familiarized with in-mold decorating, what this is it's a clear part, and this area here that is a light gray material. It's a pre-molded operation instead of a post-molded operation. That we actually put this 15 thousandths polycarbonate sheet that's finished. We put it in the tool. It's on a contour, and with air pressure and with molding pressure, we overmold. It's a finished product when it comes out. This is actually a picture of the pill box that runs downstairs in the Toshiba press. It's hard-coated. This mold, when you do look at it, just to give you a little bit of experience on it, is a little information. It's a 2-week aluminum production tool. We build it in 2 weeks. And I do want to mention that Clinton Aluminum stood behind us on this because we wanted to do a case study, and we wanted to use this mold, which has run several 100,000 parts to date. It's run in several MDM shows, East Coast, West Coast, along with Toshiba, and it's run elsewhere, as well as our facility. And Tony and Rick from Clinton, I want to thank you guys again, because that was a huge, huge help as they donated the material, and it's whole control material. The entire mold was donated. So they're actually involved with this case study as well. But this was brought up to a Class A surface. It's hard-coated. We'll run well over 1 million shots in this. It's a single cavity. When you look at the tool, you're going to say, why is this so doggone big? Well, it's built to incorporate a second cavity because we want to continue on with it. The second part you see is a medical part. And as you can see in this area here, we've got some part anywhere. It is not hard-coated. They just wanted to run 1,000 pieces, and that's it, just for studies. 1,000 pieces or less, but that's a Class A. That tool is actually downstairs. That's the part. It's a threaded component. We did that with hand loads. It's actually a mold showing the water lines coming in. This is actually built in mud base. And just showing the hand loads around where the threaded area is. Third question, how much cheaper is aluminum tooling compared to steel? That's really kind of a loaded question. The reason I say that, it depends on a lot of factors. It depends on the geometry of the part. Does it have actions? What's the life expectancy? There's a lot of things to take in when you just a generalized question, how much cheaper is it? In general, we're seeing about 30%. In some cases where the geometry is very simple, you're not going to see a great disparity. But if you see areas that are a part with a really difficult geometry that you can take advantage of cutting in CNCs instead of EDMing, sure it's going to be a lot faster. So your machine time, your polishing is faster, your EDM, we're seeing a lot less electrodes. In fact, we have what we consider a high-speed EDM sinker that's actually getting us by with one hit on aluminum. We have high-speed CNC machines that run 5 times faster than steel. We've done our own studies. This one will actually show you we're running at about 1,500 inches per minute in aluminum. This will take about a minute to minute and a half to show you, and it's going to actually go ahead. It's going to jump ahead. It's abbreviated. This is actually a 7,000 series material, 7075 that we're cutting in there. We actually are cutting a job. This is not just a case study, but we're seeing what can we do? How fast can we run? We're running as fast as we can at 1,500 inches a minute. There are different areas of the cavity that we were going to slow down. When we go to a smaller cutter, obviously you're not going to want to run. If you're small cuts or deep ribs, obviously you're not going to run that fast. You may run as low as 100 inches a minute, but this is just showcasing there's no way you can cut this in steel. We have not seen that. A lot of times also you get by with using different types of cutters, not necessarily cheaper, but you don't have to spend the most expensive when you're cutting aluminum. They do last longer than what steel does. Just getting down towards the bottom of this. the entire cavity, this is a core and a cavity, this job that we cut, actually this would take an entire day to cut a core and a cavity. That's fast. It's 50,000 deep cuts. I don't remember what the step overs are, but it's going about 0.050. It's about done. You can switch to that. Does aluminum tooling allow for undercuts from the part design? Can you build complex parts? We have discussed that. Yes, you can. Anything that you can do in steel, we've seen that we can do in aluminum. Again, these are our experiences. Maybe somebody else has a different one. This part and tool is downstairs. The reason I brought this was just to give you an idea of how fast you can turn a part like this. The part's down there with the mold. It's the only independent tool that's down at the bottom here at the bench. It's all aluminum. It's an actual independent tool. It's capable of running hundreds of thousands of parts. We're not going to because the customer only wants a few hundred. It has 6 undercuts we did in 3 weeks. The part's 7 by 12 inches. And just kind of running through this real quick, you can see there's a hand load on the A side. Covers this area. There's hand loads here and on the opposite side. B side with 6 undercuts that wrap around, that are on the inside of the part then. And actually this part does get deep coat shielding then. Another part, we talk about part geometry, how fast can we do things, what can you do with undercuts. We get a lot of it. Some of you guys might be thinking, oh, this is really boring. Of course we can do undercuts. Well, a lot of our customers don't know that. Just to kind of run through this really quick, some of these slides pretty quick here. We can see this is the A side with some undercuts here. I believe there was 10 or 12 undercuts. We've done 3 different versions, but there's hand loads here and here. And you can see there's water lines that go through the cavity blocks. Pockets for it in the B side. And then this is showing the actual hand loads. And if this is a production tool, obviously there would be lifters and cam slides. This is showing everything internally with the core. You'll see actually the part here. Then this is everything that's out on the bench. So our operators, which we have operators that run aluminum hand loads, cam slides, lifters, production, they do it all. They have to be, we use experienced supervisors. We're not using machine operators when we're dealing with hand loads. But you can see everything that comes out with the part. And then the finished part will be this. And we actually do have the parts. By the way, in the very back, so I don't forget to say, there's 2 glass display units. And there's parts inside that are not ours. There are parts that are on top. So all the parts that are in this presentation, by the way, are in the back or downstairs. So you will see there's probably over 100 different parts there. And so I don't get off too far off base. Our niche in what we claim to fame is that they're aluminum tooling prototype parts that are production quality. Okay, and you can do that in aluminum. So we're living it, and other suppliers like us are as well. So those 12 undercuts we did in 2.5 weeks. And the ignition switcher is actually a switch back there. It's a forward ignition switch. This is an aluminum production tool with 2 slides. I'm just going to show you real quick on some of the slides. Again, we can do with cam slides. So they don't have to be lifters or hand loads or hand pulls. These are done with mechanical slides. They're going to run over 100,000 parts on this. It's a medical part. Just showing the A half of the tool with the cam pins and the lock blocks. Okay. This is showing the actual core with how the slide goes over the core, then creating these undercuts. And this will be a cross-section view of it with the part then. Part being the cross-hatched area, then you can see. And everything here is aluminum, even the pins. Our cycle times reduced running aluminum tooling versus steel. Can that equate into a cheaper price? Most generally, yes. Again, we're seeing an average of about 30%. There's case studies that are done. The Honda study is on our website. We thank them for allowing us to put that on there. Their case study is for much bigger parts than what we do and specialize in. They're seeing 10 to 20% cost savings. They've switched a lot of their P20 tools over to aluminum because they've taken advantage of the cost saving. So with the thermal conductivity, the improvement in aluminum over steel, we've seen that. You don't get a lot of the hot and cold spots you do in steel. Most resins are going to process better due to this and faster. Faster cycle times equates into about, like I said, about 30%. Depends on a lot of factors. Your mold changes are going to be quicker. Heat the tools up faster, you can bring them down much faster as well. This tool actually is downstairs and it's running in the 200-ton press. It was running in the 110-ton press that I believe, I'm not sure if that's the same one, but it was actually, the tool is actually a little bit too big for the press. It's actually fit better into the 200. But this runs at 14.2 seconds. Polypro, it's a living hinge. You think, well, polypropylene, of course it runs fast, but it's got a living hinge on it. It's Class A surface. We have thick and thin wall sections. So we have a lot of factors and various issues that we deal with here, but we're proving it out that you can run extremely fast cycle times and get a good quality part. Well, again, we'll run over 1 million parts. It does, right there, it's 14.25, 14.24. Can you achieve a tight tolerance aluminum like you can in steel? This comes up a lot. Again, it goes back to perception. We get our opinions based on a perception. Can you hold a tight tolerance in aluminum just because it's soft, or just because somebody used the wrong grade of aluminum, or just because a tool wasn't designed properly? It gives a bad rap to aluminum. You can machine aluminum just as tight and hold it and maintain it as you can steel. In fact, there are studies, not done by us, studies done by some very reputable people out there, and I know that Alcoa was involved with this, showing that side-by-side comparisons between aluminum and P20 steel is that actually in some critical areas, dimensional areas, they can hold the aluminum much tighter temperature-wise, which equates out into a better quality part than you can in steel, because the steel will vary, either in injection time or the actual mold time, the mold temperature. So it's not just coming from us. This is various people that are doing these studies to prove this out. The reason I have this part, the wall thicknesses, we do thin wall, you can aluminum. It's down to 5 thousandths. I think it's up to 30 thousandths in this area here. This part, actually, the project is back there on the very right-hand display unit. There's 20 different components here, and the reason I want to show this in the presentation, the reason I brought the parts, this aerial surveillance device, it's unmanned, it's a little bit more than 3 pounds, and that's including the camera and everything. And it has to fly under certain variations that I don't know about. But the critical part for us was, it's a polycarbonate dellum part, it's 20 different components. The critical part for us was the geometry of the parts weren't necessarily difficult, but it's because of the wall thickness. But wall thicknesses are varying anywhere between, and by the way, most generally, they're around 40 thousandths. It won't get any larger than 40, but it gets as low as 8 thousandths and 20 in other areas, with tight tolerances plus or minus 2. And we signed up for this, and we're going to achieve over 200,000 design life expectancy. We're actually working with this company to do this second revision on this project. There'll actually be 3 quick slides here. This shows down where it's getting down to about 8 thousandths wall thickness right here. Same thing on this part, and I'll just show you the third. So you kind of recognize it if you do go back there and look. There's a leg. There's actually 4 different legs. So we'll go right into the video real quick, and you'll see what's critical about this part is the part weight, and it's successful. And it's all aluminum tooling. It's hard coated, and it would last more than 1 million shots. Again, I apologize. This is about a minute or so clip, and it's quite interesting. If anybody does want this presentation, you'll actually be able to hear this volume-wise. If you do want to, be more than happy to give you. We have several flash drives to hand out if you'd like. This is all controlled by an iPad. It's quite interesting. Kind of scary, but it is interesting. They're actually using this in combat. This actually was in Flashpoint in the TV series. They used it. The reason I brought this part up and in is the part's actually about 20-some inches long. And just real quick, and I apologize for not having the part here and even a better shot. I want to talk about it just real quickly. We build an aluminum tool. There's two different parts. There's the top and the bottom, and you don't really see. There's a bottom black piece here. There's more of the housing. The top part of it is actually an adhesive that they put over to get this kind of a chrome look on it. What was critical about this was the warp. We needed to hold this when we processed it within 20 thousandths over that length. It was difficult to do. We got the process. We got the gating done just right. At that time, we didn't have mold flow. We do now. But when they ran their 15 to 20,000 parts in aluminum, they went to a steel tool. The customer did. Sub-Zero is not the customer, by the way, not my customer. So somebody else made the choice to go to a steel tool. When they did that, unfortunately, they had problems. They could not hold it with the same warp specs, so they had to change something. We ran some extra parts for them while they did their design changes, etc. Again, living proof that we don't experience the same issues in many cases in steel tools as you do with, or in aluminum tools as you do with steel. Parts are back there. We've run over 80,000 parts. This is a production aluminum tool we did in 3 weeks. There's 12 different components. Number 7, is it possible to weld aluminum and be successful with its outcome? And I will be honest to tell you that there are probably people sitting here that have had some really horror stories, some bad moments with it, and there are other people here that have better experience and more knowledge about it than I do. I know that there are some people here that are doing their own studies and tests on it. All I can do is tell you what our experience has been. We would prefer not to weld 70-75 on an aesthetic area, not on a cosmetic area. The reason why is because 70-75 doesn't have the same characteristics that some of the other grades do, like QC10, Alcatel, and Elumold. They're a little bit different. 70-75, we found out that there are some hollow spots. I don't mean holes in the aluminum. I'm talking about when you put a rod to it temperature-wise. There's variances on the depth of it, and people here are more experienced than me as far as the characteristics of aluminum that can back this and tell you. We will weld it in areas of 70-75. It's not in an aesthetic area. But if we know we're going to go with a Class A surface, we're not going to choose that material. We're going to choose something else. Of course, we don't like to weld, but mistakes do happen, whether it's in the tool-making side of it or in the process side of it. So, again, the experiences have been fairly successful as long as you're using an experienced welder and they're using the proper rod and they are preparing the material, preparing the aluminum correctly to weld. So it is very successful to do this. Is it possible to run 1 million shots or more in aluminum? Of course, a lot of these grades of material, some you have heard and some not. Some people say this material is better than others. I'm just going by our experience. Majority of our material that we use is 70-75 because the majority of our volumes support that. If they're higher volumes, we're going to consider using some of the other grades besides 70-75. Not that it can't, because I run over 1 million shots in a 70-75 material, but it was also hard coated. But you have options here of other materials, your Alcatel, your Elumold, your QC10s, and these are good materials. The term production quantities, you know, again, every customer is different. OEMs, they're all different because Production for them might mean, hey, I need 10,000 pieces, some might need 4 million. Our experience for us, 90% of the aluminum tools that we've been associated with have never reached their life expectation. They sit on the shelf and they collect dust. We've seen that we can provide well over 1 million parts. Again, keep in mind you have case hardening that takes a surface hardware to hardness up to over 60 Rockwell. We prefer not to go over 60. We prefer to go around 54 to 56. It's a buildup. It does not impregnate into it. It's a buildup for us of about 2 to 3 tenths. We monitor it. How do we do that? We monitor it visibly. We also do it by our checks. We do with temp indicator. We check our wear. I had put this on there, take the 1 million part challenge, because besides some of the people that have done this themselves, Honda being one of them, is somebody needs to step out and take this challenge, and we'll work with you on it. Bridge tooling, pilot production, semi-production, it's all a lot of different things, but I do have a quick case study I want to run through. This part, it's an automotive pulley, it's 3 inches in diameter, it's glass-filled, 33% glass-filled nylon. There's no draft on the internal spline. By the way, the part's in the back, the tool is here, but unfortunately it's not uncovered. No draft on the internal spline, tight tolerance, mold size you can see, 70-75 aluminum. It's a tri-plate with 3 drops. It is hard-coated. The volumes are going to be about 110,000. So today we've run over 150,000 shots, so we're about 300,000 parts. Cycle time, there is a steel tool that's running at 44 seconds. We're not running it. We're running ours at 32. It's an aluminum, there's a steel. We completed it in 3 weeks. It's a full automated aluminum production tool with cam slides, and it runs automatic. Cost savings between the two options, 28%, cycle time savings 35% on the mold. How do we get there? Less machine time, less machine wear, lower utility costs, additional press times, on and on and on. There's a lot of advantages. This will be a picture of the part. I apologize, this area is not really well seen here. There's a spline area in here, straight up and down. There's no draft, and it's a ±1. And it's a cam slide that goes around the perimeter of the part. And you'll see some quick shots here of the cover half, A half, and the B half of the tool. We design and build our tools like what we consider production tools, our experience with production tools, and we stand behind. If we run it for another plastic, or build a tool for another plastic company, they're going to be involved with it if it runs at their facility. We want to make sure that it's designed how they want to run it. But for us, this is how we built it. We actually have water that comes up with bubbler in the core itself, coming up from underneath. Cam slides have water in the core. By the way, you are seeing some hard coating out here. Why is there a different color variation? There's a better picture coming up here. You might be able to see a little bit better there. This is this raw aluminum here. This is aluminum also, but it's hard coated. So the outside parting line is not, because we're not using that area to shut off on anything. Our aluminum kiss-off is all within this area here. The case study summary, just to give you an idea, there was only about a $12,000 cost savings between a P20 tool that they had built that was done in 5 weeks of P20, and ours was $22,000. So it was only very little cost savings. When you run this out over 5 years at $110,000, it equates at only, what, $55,000. Total savings was only $67,000, but look, that's one part, and that was a low volume, and that was only a 2-cavity. Multiply that by, if you're running 100 different tools for a customer, what that could turn out to be. Points to consider for aluminum tooling. And again, every design and every project may not fit aluminum. But I want to go through again our experience. Beat the competition. You achieve the mold cost savings, your product savings, your product quality most generally. I've yet to see a part that we do in aluminum that is worse than what somebody can produce in steel. Minimal warp and better dimensional stability. In some cases, lower clamp and injection pressure, again, depending on the material, depending on the part geometry. Quicker mold changes we discussed. Your CNC machines run up to 5 times faster, we've seen. Less wear on cutters, less electrodes. You can hard anodize nickel plate for critical areas. Products that we produce successfully is your high gloss and chrome plated and texture. We cover these. I'm going to go through this quickly on some of these pictures. There's a living hinge in here. We talked about Ultim, insert molded parts. You can do in-mold decorative. You can do your TPs, your Sanaprines, your soft touch PVCs. I put down deep straight walls. We might have a picture of it coming up here. There's a fan. And it's about 4 inches in depth. And we had very minimal draft allowed on it. The customer needed us to maintain, I believe it was like a 1/4 degree. We had to we hard coated it with 9-bore, which is lubricity hard coating, which helped us a great deal to eject that out of the cavity. So we'll show that here in a second. And also you can do threaded components. We have some in the back. Living hinge part, which is the same tool that we have downstairs. There's a living, not this one, but there's a living hinge downstairs. This one as well. Soft touch TPE material. This is an insert molded part. We only have horizontal presses, so we're not doing this in a vertical press. The reason I have the part here as an example is because there were 18 different inserts in this area. Very thin wall sections. I believe it was down to 12 thousandths in areas. This is in a rigid PVC. We inserted it for gas purposes to make sure it's vented properly is why we did that. This is the part I wanted to show real quick that we used on a 9-bore that allowed us to eject out of the tool properly. Before I talk about this one, there's a tool, and I don't have it in the presentation. I just thought of this. When we talk about 9-bore, we have an 8-cavity aluminum production tool, and we are running at 50% velocity before we hard coated it, and it was running 32-second cycle. After it was hard coated, we were able to reduce that velocity down to 25% and the cycle down to 28 seconds. So there is also other advantages of this hard coating. I'm not here for Bale's purposes. They do help us a great deal. But this process is a very good process to consider, not just in aluminum, but also steel. This is an insert molded, so in-mold decorative part, polycarbon PCABS. Another one, this tool actually is downstairs. It's a 2-cavity tool. You'll see a first shot and you'll see a second shot, and it's an overmold soft Sanaprine on polycarbonate. Automotive acrylic resin, we do either polycarbonate or acrylics. This is a light pipe, Class A surface. Very small medical component with cam actions. This part is an automotive bezel. It's PCABS. It had 22 lifters. They were expecting to run about 60,000 pieces on this. We had 22 lifters on the underneath side. They were purchased components, and we hard coated it, so it was the purchased component was hardened also, so it was hard on hard. The reason I've included this clip is, and I have always on the presentation, because I think it's interesting and maybe even funny and maybe even frustrating, because here's a guy, Doug Bryce, and he's involved in this, one of the studies that Alcoa was involved with here recently with some of the information, and I think they were quoted, they even quoted this guy. It's interesting 14 years ago that he was talking about the cost savings in aluminum, and you're able to, not just in the tooling, but the molding side of it, but also you can case harden it. This guy was involved with the study, and IBM did a study back in '98 as well, seeing the same things. And why is it taking so long to jump on the aluminum bandwagon? It's based on perception, perception, perception. Okay. Just to summarize, used today for cycle time advantage and lower tooling costs. high-strength aluminum alloys are making a huge, huge impact in all these industries. We're seeing it. Our customer base is more and more taking advantage of the aluminum cost savings that we can pass on to them. Some are still not, and that's okay. That's what they choose. Aluminum is not just a bridge to a faster product, but also it's a successful alternative to steel. It's not for every application, it's not for everybody, but we're seeing that there are huge, huge advantages and great alternatives and cost savings for customers on products. And I guess just to my final little clip here, and I'm not going to read it, you can read it. I think this is kind of interesting because it kind of falls in line with kind of what we're talking about, is trying something new and not being afraid to try something new. Again, just our experiences. And we don't know everything about aluminum tooling. We don't know everything about plastics, and we're not saying that. It's just the 35 years of experience that I've had and we've had as a company in aluminum and production tools. That's my presentation. I guess I want to open up for questions. Dale, is that correct?
Yeah. Bob here. One of the things that aluminum tool lends itself to is you get a leg up on crystalline materials to be able to control the rate of cooling, be able to control the crystallinity and the sizes. In the case study that you had with the pulley, where you had 32 seconds and 44 seconds between the two tools, what was the difference in rejects based on more?
We aren't running the steel tools, so I can't tell you the difference between.
Okay, I
yeah,
thought maybe you
that's
had
at another supplier. Okay. And actually our customer contracted that to another production house, and they actually built that tool prior to our aluminum tool, and they were unable to keep up with capacity. So they came to us for this 2-cavity aluminum tool, and which is outperformed. But the answer to that, I can't tell you what the differences are.
Yeah, I guess that's another thing in the criteria, if you will, or the advantages of aluminum is that it's going to reduce your reject rate.
Right, you know, there was, I think it's in mold making technology just recently, I think it was last month, there was a case study that was done. Again, I bring up, I think Alcoa was involved with his aluminum group out, I don't know if Dave or somebody knows, is it Dave Banks? Dave Banks. And there was somebody else too involved, I think Ron Mercedes from Alcoa was involved, and they did this study, and I know there was direct comparisons between aluminum and P20. It's a very good article, and it might answer that.
You mentioned better material flow with aluminum tooling. What do you attribute that to?
Well, the thermoconductivity. I mean, we're able to get the material, and again, this study comes back. They were kind of giving us the same information. Is that with the aluminum being able to maintain the heat much better, not having a whole hot and cold spot flows in there. They thought actually it was going to crystallize, or because of the material temp, but it wasn't. Actually, it was the opposite. Because of the flow of the material and the material of the aluminum itself being more consistent, not having the hot and cold spots, you're able to achieve just a better flow of material. Yes?
How do you feel you compete with features that can be EDM'd in steel versus cutting, or are there any limitations?
Well, the problem would be maybe in with the EDM processes, can we cut it because we will have a radius left, and you need a sharp corner, so you can insert it or you can make electrode and burn it. But that would be the geometry difference. But as far as a direct comparison, obviously you can cut something much faster. You've got to cut an electrode, and then you've got to set it up, and you've got one shot to get in the right location. Right. So, I mean, you have great advantages to cut something because you're going to cut it faster, you're going to cut it one time instead of a few different setups.
I guess I meant, you know, deep drawn features where you would need a sharp corner, so you would insert that?
We would, yeah, we would have to insert that, or we would burn it, because we have conventional tool making there as well, so we do have an EDM also. Okay. So we would, in that case, we would burn that. You know, depending on, is there a draft on it or no draft?
Okay, thank you.
Yes?
Some of the issues we have versus skateboard versus aluminum tool is the flash. And
not sure that I understand, I didn't completely hear everything, but from what I understand, is this a tool that's aluminum on aluminum, or is there steel in it as well?
Yeah, it's aluminum on aluminum.
Okay, okay.
Okay, and we have similar parts in steel also, P20 versus also in fully hardened.
Okay.
But when the aluminum tool flashes, what we don't know is that flash is due to the parting line wear off of the aluminum itself, or is it because of some of the details are expanding in the
Yeah.
in
Sure.
the cycle.
Yeah.
You're showing a slide where the two of the slides are crossing, going and crossing and kissing off against each
Yes.
other.
Uh-huh.
So those are thin details. It can expand, because what I'm saying is, if you some mold makers take the seal of test on a bench and then you put that tool on the press and run it, the seal of is different.
There's a lot of speculation.
A lot different than a steel mold. So
Yeah, a lot of speculation though on this, because we're talking two different tools. We're talking aluminum, steel, but could be just, it might come down to tooling practices. How did they build the tool? Did they build it with more clearance? I don't know. Is there wear? Do you see wear on it? Does it have the proper draft on shutoffs? There's no doubt on parting lines, you have to be careful. You can smash a P20 or hardened steel tool just much like you can aluminum. So there's actually good practices that have to take place either way. I'm not sure that I'm really answering your question, but it's kind of a loaded question without really knowing, without really seeing it. Anybody else? Sorry. Yes.
Bob, share any experiences, if you can, for us on the repair. If in the unfortunate event aluminum tool that's been coated gets damaged, can you share any experiences as to how you've went through weld repair or repair of the tool when it is a coated tool?
First off, when it is hard coated, you can get it stripped.
Okay. And you've had good success with that?
Absolutely.
Good.
Yeah, not a problem at all, and it's a fast process, and it's a very controlled process as far as stripping it and then recoating it. You can either weld it. We prefer to weld it, obviously uncoated, because you have that factor in there, and why involve some other factor? But yeah, we've had good success with that, and then we recoated them.
Thank you.
Yes.
Talk about case hardening, considering parting lines. Case hardening is only so thick. You still
Correct.
have the softer aluminum underneath. Passing counting the parting lines, you expect you're going to lose your edge more quickly than if you want to go in a hardened tool.
Well, to back up, we're not pounding parting lines. I understand what you're saying, but you get the concept again, perception. We're not trying to smash it. Obviously, we got the set point on your clamp, such, and we do not take the practices initially that we want to run the tool initially and flash it to see where we're at. We do not use those practices. Okay, we want to clamp it up properly. But to go back, if you hard coat that and you're at 54, 56, 60 Rockwell, and P20 you're at 28 to 32 Rockwell, that helps you right there, but you do need to make sure that you're monitoring visibly and also dimensionally to hard coat, because it does wear. I will say on a two cavity, the part is back here, apologize. It's a two cavity run about 330,000 parts on today, is we have had to strip that and recoat it, and it was primarily in the straight spline area, because there's no draft. And it is on 33% glass fill, but that's a different situation, is that it's not even steel on steel or aluminum on aluminum. But it boils down to whether it's a P20 tool or hardened steel, you still have that. You have to monitor. You know what? You can go up steel just like you can aluminum, right? So it does boil down to, I guess, the experience we have because we have so much of it. Maybe we take some things for granted. We try to use the same practices in steel or in aluminum that we do with steel or have with steel. So it's kind of an apples to apples comparison, I guess. Yes?
Do you find that in practice, when processing, when you first start up, or when you first start doing this, that your cooling line temperatures that you're normally using compared to what you used to use with steel and what you use now with aluminum are significantly different because of the reduced thermal gradient?
We tried, yeah, that's a good question. We try to use the resin specifications for setting those parameters, but they do have variances on there, even in the stock temp, let alone old temp. What we've found is actually we can actually run the mold temps a little bit lower. We try not to. We try to use the same practices that we're used to in steel, in aluminum. But what you can see though is that you maintain, if you set your thermolator at 140 degrees, it's not, and if you put a parameter on the tool, on the aluminum tool, it's not going to vary more than about 5 degrees. Try that on steel, and then take it all the way around the parting line, and tell me what you're going to get. You're going to get up to 20 degrees easy variation.
I think this is why you would usually end up trying to run a lower cooling line temperature of steel mold with, you know.
That's true. Right, that's a good point. Anyone else? Yes?
Do you need to stress relieve the aluminum after machining so that the features won't move when you bring it up to temperature?
That's a really good question, and we have done that before. It depends on the part geometry, the depth of it, and how much of it we're going to cut into aluminum. It kind of varies on the type of material of aluminum that we've found that we've used as well, but we have stress relieved that before. Obviously, you know, with aluminum, you're going to cut it. You're not going to send it out to get heat treated. It's not going to come back. You're going to grind it. You're machining everything. You're finishing it. Yes, you can grind aluminum. You typically don't. You can though. But to stress relieve, yeah, in certain cases, yes, but it depends on the part geometry, the depth of the cuts, and how much you're really hogging out of something, because you are putting stress in the material, whether it's aluminum or whether it's plastic. Well, that's a good question. Yes?
I work on a lot of optical quality parts. What's the maximum polish levels you're able to achieve?
Whatever Bale's mold can give us. And I guess I'm being honest with you about that, is they say they stand behind a Class A1. Is Harry here? I don't think Harry's here. Harry from Bale's, Harry Ramondi. He's a great guy. He'll give me the best polish job I've seen in the world, and he's going to tell me, I don't know, Bob, that's an A1 to A2, I don't know, somewhere in there. Bottom line is, we have lenses, light pipes, Fresnel lenses, that we can achieve a Class A surface on. And
with aluminum on the optical surfaces.
yes, yeah, it is aluminum. It is aluminum, and it is, we'll say, it's going to be hard coated, because to put the final finish on, it needs to be hard coated.
Of course.
Yeah, we have aluminum tools, polished to A1 finish, pretty close to A1 finish without hard coating.
Okay, yeah.
And
You run a lot of parts?
Maybe we run a lot, maybe 10,000 to 15,000 parts.
The reason we like to do that is also to protect the finish, but we do that also because they also prefer doing it that way to bring it up to the final surface finish. Yes?
We make a lot of laminate positional molds for connectors. Like, we want to connect with 2 positions versus 100. That would be the same mold, just different laminates that we insert.
Okay.
And those laminates are ground to like 20 millionths. They're very few tenths, very small. How would aluminum hold up to that?
How would it hold up to that?
Yeah, like the very small grind detail and the changeover for repeatability for different positions.
So you're saying within plus or minus a couple tenths, or within 2 tenths?
Yeah, less than that.
Yeah. In a situation like that, you have the option, we have the option to cut that on our machine. We also have the option to grind that. Again, if we're going to mold that, we're going to be a little bit concerned about holding something within a fixed tenth. Mold that, but tooling-wise, we can be able to achieve that. Yes?
Due to the better thermal conductivity that you've shown us with aluminum, have you ever run into a situation where you've molded parts from a prototype and the customer's going to build a steel mold and the shrinkage values are different? If so, do we have to factor that in?
That's a question. It's probably, if there are some plastic companies here, some manufacturers here that have had that experience, they may have some different than myself. We really haven't had too many opportunities where we build aluminum tool and we run the steel tool now. We just don't build steel tools. So we have that disadvantage right there. In the past, we have run steel tools and can tell you that there are some variations in that. And depending on who you talk to and the studies that are showing, and I'll stand behind the studies that I'm familiar with for myself, is I feel that we can maintain and hold a critical dimension as well, if not better than steel. Does it affect your shrink because of aluminum and steel? And why would that be? In my opinion, that would be, if there is variation, it would come from the steel tool more so than the aluminum, because the aluminum is easier to control.
I'm just wondering if that's something that, and obviously, that you would need to factor in, since the aluminum has better conductivity, it's gonna pull the tighter tolerance part. Now you build a steel tool, is there a relationship that you would recommend moving in that direction?
The problem with, there's thousands of different materials out there, resins out there,
Sure.
and part geometries, and what's your tolerance, but yeah, I understand in the material flow, how is it gated, there's so much variations there, but they're probably, I'm sure that's a good case study. I personally don't have the experience to say, yeah, you know what, it's gonna vary on polycarbonate, it's gonna be 1,000ths more per inch shrink because, what's your wall thickness? So it's wide open.
I think, answering your question a little bit, if you did a mold flow analysis and you looked at the mold temperature on the steel versus the aluminum, you're gonna see the different temperatures, and especially if you're gonna handle the crystalline materials, you're gonna have a difference in shrinkage because of the difference in crystallinity. So,
You know what, yeah, Bob, that's a good point, and you are right. A mold flow will show you the shrink rates, the resin, gate location, and type of material. That's a good point. That's a good point.
And the warpage.
Yes, warpage as well. You'll see that ahead of time, and that's a very good point on the mold flow because it does show you that.
The problem you're gonna run into when you go from aluminum tool to steel tool is that because of the different thermal conductivity of steel tool, you won't be able to maintain the mold temperature as well as you could with aluminum tool.
Right.
And you're not probably ever going to be able to. So that means you're going to have hot spots in the steel tool that you would not have an aluminum tool. And then the crystallization would be reflective of that from the steel tool much more so than aluminum tool.
Yeah.
So if you could maintain the thermal gradient in the steel tool, theoretically you'd be in really good shape to transfer from aluminum to steel. But if you couldn't, if you couldn't, then
right.
you'd have to make sure that you could, or
Right.
at least achieve or get close to it.
Right.
Yeah,
I
that's
think
a
you'd
good
only
point.
find that out after making.
Anyone else? Well, these are great subjects, and I've got my marketing manager here that handles it, and she's gonna kill me. There's a lot of good questions and answers here, and there's a lot of stuff that can be put on blogs, and there are people out there that are looking for information. There's, your there's plastics today, your mold making technology, modern plastics. These guys are looking, just give me some information. But you know what? I need some OEMs, some reputable companies that stand behind you, little guy, to say, yeah, he's right. But there is a lot of good information out there about this, and we're getting closer and closer on it. Anyone else?
Bob, just one other
Yeah.
comment. As we went around with the PSG presentations, there was a company that, I think it was Steelcase, that basically in aluminum came very, very close to a conformal cooling. What they did was they came in at odd angles with the cooling lines, and because of the thermal conductivity of the aluminum, was able to, I'd say, get 90% of what you could get to in a conformal cooling tool. So if you're willing to look at cooling lines out of the box, if you will, you can build an aluminum tool with conformal cooling.
Good point. Anyone else?
Got a question.
Yes.
We do a lot of in-mold decorating for the company I work with. And we've tried aluminum in the past, and we find out that the aluminum cools down a lot quicker when that mold sits open. Is that something of a fallacy based on what you're saying today?
You can see it. Is the temperature still, thermolator is still turned on to the same temp as
It sets at 120, and we saw it drop down about 10 degrees.
Huh.
This was in a 500-ton press.
Yeah.
We were
No.
making labels for Whirlpool.
You know what? Maybe the platinum's sucking some of the heat out of the material. I would say that, to be the case.
Okay.
You can use those plates on the back of them, much like if you're running a hot runner system. So, that would help you. Okay.
Thanks.
I'm sorry for butting in, but another technology that would help that is if you went to pulse cooling, where basically you are bringing that in just at the point of time when you're injecting the material, and at that point you've got everything coming together at the same time.
Okay, good suggestion, thanks.
Anyone else? No? Okay, well, you know what, thanks again for coming, everyone. Appreciate the time and everybody's questions and the attention. Thanks a lot.